You will share feedback link also during the session. Today, Abindal sir will deliver talk on convolutional neural networks, popular research topics, and future directions. Sir, please start the session.
Yes, ma'am, sure. Yeah, good evening, everyone, and welcome to day 6 of this FDP course, Foundations of Machine Learning and Deep Learning. So, today we'll be discussing about convolutional neural networks. So, in the last few days, we've covered a bunch of different algorithms. We started off with some basic machine learning algorithms like logistic regression and naive Bayes. Then we moved on to the state of the art algorithms, which are boosting and bagging algorithms. Then, yesterday, we looked at a different type of uh, algorithmic subset, which is the deep learning, where you use something called as multi-layer perceptrons, which are nothing but your artificial neural networks. Then we talked a bunch about how these MLPs are trained, what is backpropagation, and then we talked about how different types of techniques can be used like cross normalization, dropout, regularization to help the MLP training. So today we'll come into a slightly different, again, different type of neural networks called convolutional neural networks. These type of neural networks are very popular with images. So in today's world, if you take at any algorithm that is taking input as an image, most of them, 90% of them will be using convolutional neural networks in some form of the other. In fact, I would say 97, 98% of the algorithms which are there in today's world. So these are very important to know if you want to learn about any of the state of the art algorithms that are present in today's world. So as usual, this is what is the classification task. I think by now everyone is thorough in this. What the objective of a classification class is. It's basically to identify a classifier or a decision boundary that separates the classes in different settings, either binary or multi-class. Then we also talked about regression, which is nothing but trying to find the best fit line that explains the trend in your data. This is nothing but the red color line that is explaining all the cross data points. Like I said, these are a bunch of different algorithms. So today we'll start off with the last where we stopped yesterday, multi-layer perceptron. We will see why multi-layer perceptron fails at certain situations, mainly when the input data is images. And then we will see how convolution neural networks can overcome these limitations of multi-layer perceptron and how they can learn better representations. So yesterday, if you remember, we talked first about a perceptron, which was a very simple single layer, multi-layer perceptron. We can say a single layer perceptron. It's just one node in this entire. Sorry, is this one node in this entire network? And what did the perceptron do? It took inputs along with some associated weights. It summed them, and then there was a simple activation in perceptron, unit threshold activation. Whereas in MLP, the activation was non-linear, like ReLU or sigmoid or etc. So today let's look at why people shifted from multi-layer perceptrons to CNNs, especially in the case of images. So let's first examine what are images itself. So as you can see on this slide, this is a simple image of a cat, which we encounter in most of our day-to-day life, right? Even any picture which you take, which is there in your phones, right? Those are all images, and all images contain something of this structure. So if you look at a small patch of this image, like the highlighted patch, it is nothing but a matrix value, which is each of the value inside that matrix is a pixel value. So if we go into a little bit of details, okay, so this matrix value, and each of these value is a pixel value. Each of the element in this matrix is a pixel value. What is the range of the pixel values? It is usually 0 to 255. So any value between 0 to 255 is the valid pixel value for a normal image. And then there is a difference between two types of images. What you'll see is called a color image or RGB, where your matrix will have three dimensions. So what do I mean by that? Let's say this entire image is of the size, if let's just say it is 32, and this is also 32. So the dimension of this particular image will be 32 comma 32 comma 3. So this last dimension is 3 because of 3 different channels: red, green, and blue. Now there's another type of images called your black and white images, and they have only a single dimension. So to represent black and white, you just need 32 comma 32 type of a matrix. So these are the different types of images that are mostly possible. And each pixel value, obviously, there are different types of data structures that store these images in different types of data types. Like some use integer, some use some U integer, a bunch of different data types are needed. So this is how your image is stored in your laptops. Now, like I said, these are matrix, right? Till now, when we saw a data set, if you remember what, like, let's take iris data set, the plant data set, right? What was the data set like? So there were 4 columns. This was like sepal width, sepal length, uh, sorry, sepal length, petal width, and petal length. And then there was this class. So we'll ignore this last one. We just need the input features, which are these 4 features. Now, when I was sending an input, right, if you look at the previous figure, so here this input for the iris data set, how many values will it be? It will be just 4 values because of those 4 features. So x1, x2, x3, and x4. Now, this is fine if your data is something like your CSV data for iris, like that Excel sheet type of data. But for images, this is obviously not true, because images come in a matrix, right? Images, like I said, they come in some 32 comma 32 comma 3. So what do you do in that case? We do something called the flatten operation, which is nothing but basically converting any high dimensional vector into any high dimensional tensor into a simple vector. How do you flatten out? You just multiply all the elements and make it a big vector. So in total, you'll have these many number of elements in your vector. So it will be a very big vector. The input now for images will be a very big vector, which is of the size 32 into 32 into 3. So, do you see any problem by flattening out an image which is previously of the matrix tensor size 32 comma 32 comma 3, and making this vector, right, of this and sending this as an input? What do you think will be a problem? What is the immediate intuition that you get when you flatten out an image and make it into a big vector and send as an input to the network? What do you think will cause a problem? Any ideas, any guesses? Okay, so maybe I'll explain that part. So one immediate problem which you can see is the loss of relation between the different pixel values in an image. So what do I mean by that? Let's look at the cat image itself, right? So if the eye, so if one, why is it not right? Okay. Okay, let's take an eye of this cat. Now the pixel at this particular eye and the another pixel values at these particular eye, they both have something called as a spatial relationship. What do I mean by that is, usually eye comes in pairs for any cat, right? And they're also separated by a certain amount of distance between them. So that type of a relation which you have from between 2 pixels, right? When you flatten out a vector, when you flatten out an image and make it into a vector, those spatial relationships are lost. It's not just between eyes, even the ears, for even the ears, if you take for that reason, yeah, even ears, legs, whiskers, mouth, anything whichever we human beings need to understand to make it a cat, right? Those all informations will be lost when you flatten them and make it into a vector. So this is one major problem that people faced when they were when they were using multi-layer perceptrons for images. Now apart from that, there is another problem which we will see in the next slide. There's something called as parameter explosion. So like I said previously, whenever you had the data, right, what was the number of features which we had? Like, let's talk about the heart disease data, wine quality data. Max to max, you had 20 columns, 60 columns, 100 columns. But for an image, like I said, a simple to simple image is like 200 cross 200, which is still a very blurry picture in today's world. When you click any HD picture and all, right, it is more than like 2000 cross 2000 pixels, 2000 cross 2000 pixels. So HD pictures are very high quality, right? But let's assume even 200 cross 200, very simple image. Even for that, when you flatten it out, and this is a black and white image also, this is not even color image. So there's only one channel. When you flatten out this black and white image, you'll get 40,000 what do you say, hidden or input vector size. Now this 40,000 will next be mapped to another input size. So you need to understand the number of connections that are being made, because let's so let's say this part is 40K, and then there'll be a bunch of different which is greater than 40K. And if you remember, in multi-layer perceptron, every node will be connected to every other node. So easily, like mentioned, these will go beyond 2 billion parameters. And you need to understand that this is not even a big task. You're simply doing a simple image classification task. And for that, if you use something like a 2 billion parameters, then for complicated task, you need to forget about, like easily it'll go into zillions of parameters. So that is not possible to train in today's world. Even the biggest of the biggest parameters models which you have today are some, I think, trillion order, not more than that. So that is another big problem for using images for multi-layer perceptron. So these are the two main reasons: spatial correlation is lost and waste of resources. So to overcome these, people came up with something called the convolution neural networks. So the idea behind convolution neural networks is very simple. So this is a typical architecture which you see. It still has at the end a multi-layer perceptron, which we call the fully connected layer. But before that multi-layer perceptron, we have some convolution layers. I'll explain in detail what a convolution layer is. But just see that this is a typical type of a CNN architecture which is used to learn the features from a input image. Now let's understand what it is looking at. So let's try to understand first the idea what we want, and then we will see how the convolution itself works. So what do we want? Two things we want. One is the spatial invariance, which we call. So what is spatial invariance? If you see a dog, like let's assume you are looking at a picture of a dog, which is not the only thing present in the image, but let's say dog is present over here on top of the image, and some random objects are present over here. Now, if you look at this dog, you know it is a dog which is present at the top left corner. Now, if that same dog is present somewhere in between, middle right, you still know for a human being that this is a dog. Why? Because we look at something called as local relations. So, what is the local relations? Like I said, a dog is associated with certain things like a body and a tail, the ears, the eyes, the mouth, and all of these usually lie in a local area. It's not like the body is here, the tail is somewhere in the down. It's not like that, right? A dog comes with all its pixel values which are related to each other in a local patch or local area. So for human beings, we actually, this is how actually human vision also works. That is where these they took inspiration to make these CNNs. So for human beings also, we keep on looking at certain patches in an image, and then we keep on extracting information on all these local patches and combine. In like in first layer we just look at this local patch, and then we separately look at these local patches. In the next layer we combine the features learned from these two local patches and make another third patch. So in that way, hierarchically, we keep on creating more and more complex features from all of these local patches. So that is what human beings also look at. So that is what CNNs also do. They try to first look at a local patch, learn what are all the important features, then they do this for all the different patches, and then in the next layer they again combine the information from the previous patches and make a third patch. So in that way they keep on building and learning what are all the important features. So in those ways they're able to identify the spatial invariance, because now they're looking at a local features. Similarly, there are other local dependents that is there, like uh, for let's say this is some animal, you don't know whether it's a dog or not, but you see a kennel, then you make associations. Okay, what is usually around a kennel? A dog. So this type of again local information is also preserved in CNNs. So these are bunch of different motivations by what people needed from in the way that CNNs should work, and that's how they came up with this simple operation called convolution operation. So the convolution operation is also existing in electrical field, convolution and correlation. So this is not the same operation. This is a more slightly easier version of the operation. In convolution operation, I think in electrical field, you have to first rotate your filter 180 degrees, and then you have to place it on your input signal, and then you have to multiply, do element wise multiplication summation. Here you don't have to worry about all those things, because the point over here is this particular filter, right, which we have, these filter weights are unknown. These are the weights now. This is what you need to learn in the training process. So it doesn't matter if you do rotation and flipping before calculating convolution value. You just assume and that there are unknown values, and you just do simple element wise multiplication and addition. So let's look at the first output value. How do you calculate a first output value from convolution operation? You just take this kernel, you place it on the first 9 or 3 by 3 patch on the input image, and then you do simple element wise addition and multiplication. So 7 into 1, 2 into 4 into 1, 3 into 1, then 2 into 0, and so on, so on, so on, so like the values which you see on the bottom, right? And this all you sum it up together, and the final value which you get, that will be the output. Okay. So as you can see, this is a simple convolution operation. But one thing which you notice is after doing convolution, the size decreases. But sometimes I don't want my size to decrease. I want the size to be as it is, because there are many benefits to keeping the size as it is, because then you can have bigger and bigger networks. Because if the size keeps on decreasing, then there is a limitation to how deep my model can get. So sometimes I want my size to be the same, output size to be the same as the input size. Any guesses how I can do that? So this is a standard operation, I think, in any signal processing scenario. How do I get the same output size as the input size when I'm doing a convolution operation? Any guesses? Okay. So the answer is padding. So if you want to, so for example, let's look at padding scenario also. So let's say the input is what? Input is 5 cross 5. What is my output? Output is 3 cross 3. Now if I want my output to be 5 cross 5, what should I do? Very simple. You just add values over here. Zeros. This is one type of padding. There is also another type of padding where you don't have to add zeros. You can add some this last layer itself, you can invert and add, but those are all different complications. For now, you just imagine a simple padding to be a zero padding. Now, only one layer of padding won't work. You need to add another layer of padding. So similarly over here also and here also. So now when you place, your first 3 cross 3 will be on this. This will be a first operation. Now your output will be a 5 cross 5 value. So this is how padding usually works. So if you want to maintain that output size to be the same as the input size, you just do padding. So appropriate, don't worry if you don't know what is the appropriate value. Sometimes I might also make mistakes in calculating. But as usual in code and all, you don't have to worry. You just mention padding equal to true and PyTorch will take care of everything. But just understand that there is a concept like padding, which helps you maintain the same dimensions for input and output. Okay, but let's understand what are these convolution even looking at, right? So easy and the best scenario to understand this is looking at these operators called as edge detection or Sobel operators. So these are particular type of filters which detects edges from an image. So why does it detect edges from a filter image? Because let's look at the way the filter itself is constructed. So this particular filter, sorry, yeah, this particular filter has positive values on the left side, 0 in between, and negative values on the right side. Now let's say I take an input image. Okay, and I have a edge over here. And in another scenario, there is no edge in this local patch. In this local patch, there is an edge. Now imagine I place this filter where there is positive values here and there is negative values here. Now similarly on this also I place positive values and negative values. I'm just placing this filter on top of these two different patches. So over here, sorry, actually the edges are more wider. It's not this just like this. It's more wider, let's say. So here when there is a shift between the algorithm, because this side there is some value like more intense values, pixel values, whereas on the right side there is less intense pixel values. So when you do this operation where you multiply each term, the convolution operation where you multiply like +1 and this pixel value x1 then plus 2x1, so and so, plus another x2, and plus 1 x3. Similarly, you subtract another values x5, x6, and x7. Since x1 and x2, x3, and all these values are not equal, so when you subtract them, you'll still get a value out of it. You'll get some positive value out of it. Positive, some value you get out of it. So that means there is a shift when you're going from your left side to the right side. It means there is some edge that is there. That is how you detect the edges. Whereas if you look at this empty patch, the pixel values are all the same. There's a smooth gray texture, you can assume. There is no edges or bumps. So the pixel values will all remain the same. In that case, all of these terms will get cancelled out and you will not get any output. So it will be a zero value. Whereas for this, you'll get some positive value output. So for this case, so that is why these type of detectors are used to identify the edges in a particular image. Now obviously there are two types of edges you can identify: horizontal edges and vertical edges. To get your horizontal edges, you look at this particular filter. To get your vertical edges, you look at this particular filter. So this is the same thing what I explained on the bottom with respect to values. So they place this particular filter on this first part of the local patch of the image, and then they just calculate the values. Let's look at more visual example. So this is what it looks like. So let me zoom in a little bit. So this is the input image. So what are the edges? These are all like the edges over here, right? So this is all edges. Anything that's a picture shift in the pixel values from left to right when you go, those are all becomes edges. Even these corners are edges. So bunch of different edges. So that's what is being detected. If you can see, the white dots are all the output of the convolution of the Sobel edge detectors. Similarly, here you detect all your x direction. So you don't have to separately detect x and y. You just can detect both of them together by taking the magnitude of both the gradient values, and then you can just do a summation. That is also possible. Then you can just take the magnitude of x detectors and y detectors, like root of x square plus y square values. That is also possible. Okay, now let's come back to the convolution. I hope the idea about what is a convolution, how it works, that is all clear. Any doubts in that part? Anything that is unclear about what is the motivation behind convolution, or how the operation itself is done? Anything that is not clear? Okay, great. So if that is clear, let's move ahead and let's look at the network itself. So this is a typical CNN architecture. You remember this input data? I think in your logistic regression class, you looked at MNIST data set, right? Which was nothing but a bunch of images which contained a single digit, and those digits ranged from 0 to 9. So this is a standard digit classification task, which till date people still use it. It's a popular data set for doing some benchmark results analysis and all those things. So this is a image which contains it's a black and white image, and the size is 28 cross 28 cross 1. So what is your task? Your task is take this input image, and your output, you have to predict whether it's a any one of these digits 0 to 9. So how do you do? You first take a small kernel. What is your kernel size or filters? Kernel, filter, these are all the same terms. So don't get confused if I say kernel once and filter once. So you take a small kernel, 5 cross 5. You do necessary padding in this case. Yeah, and then you do this convolution operation, and then similarly you do another operation called max pooling. I'll tell you in the next slide what max pooling is, but for now you just assume that max pooling is an operator which is happening, like it's just like convolution but a variant of it. Then you do another type of a convolution, which further and then you then do another max pooling, and after this max pool, now this tensor, right, 4 cross 4 cross n2, you can flatten this tensor out. You can it'll be something like 16 n2 values. This entire green color will be 16 n2. Now this will be as an input. This will be sorry, this flattened layer is that 16 n2. This will act as an input to the hidden layer of the n3 units, and then you have an output layer. So here it is good to flatten out, because now you have learned most of the important features you could in the first layers, and now those features are enough, and those can be flattened out. You have separate features like most of the textures and all you have learned. So that is fine, which have been learned for CNN. Now it's okay to flatten out because your size is very small also. So by flattening out, you're not creating any complex parameters explosion or anything. So this is how a typical convolution works. Let's look at the pooling only. I said that there are two types of poolings, very simple to understand, called max pooling and average pooling. So what does pooling say? Like you have to always give an input image, input filter size of the pooling. Let's say I have a 2 cross 2 filter, and then what does pooling say is you take this 2 cross 2 filter, like I'll just draw that filter for ease. Mm, okay, let's say I have this simple 2 cross 2 filter. Now I place this filter on the first patch. I place it over here. Okay. Now max pooling says just pick whatever is the max value. What is the max value in this local patch? 9. So that will be the output. Now next you place it over here. Then you identify what is the max value, 7, like this. This is max pooling. I think you understood what average pooling will do. Average pooling is nothing but it takes average of all these 4 values. It'll take average of, next time it'll take average of all these other 4 values. So in this way, pooling operation works. There's one other term which I didn't explain called as stride. So stride is nothing but how much you should move this filter on the input image. So what do I mean by that? Let's clear this. Okay. So previously, if your stride was 1, you just have the input filter here. And in the next iteration, your input filter should be ideally here. Your input filter should ideally go here. This means that your stride is 1, that you're moving just 1 pixel to the right. But you can also define that in this case, if you look at it, we mentioned stride equals to 2. That is why I said don't look at the next stride, skip 1 right and go over here and place your object. So that depends on your stride value. So the bigger your stride, the output size will be very like the output size will keep on decreasing if you don't do any padding. So stride and all these things make sure that how much type of what type of convolution happens, how much information you should gain from these convolutions, and etc. Okay. So this is a simple pooling operator. And now let's look at what the neural network itself learns, like what is happening. Let's try to visualize it. So this is a standard technique people use. Basically, they just plot that filter. These are all filter activation outputs after the filter. So they just plot the outputs after doing convolution and see what are you even observing. So let's take an input image car. Now let's try to zoom in. Yeah. So as you can see, you see different outputs, right? Different convolution filters are capturing different things. This first part is just capturing edges, like a black and white type of an edges, just the outline of the car. This is capturing more of a blurred form of a car. This is capturing certain other features. So in this way, you can see a bunch of different features are captured at first level. Now, those features will be more complicated as and when you go further. So now, because you're doing convolution on these input features now, right? Now, the features learned will be even more complicated. So beyond a certain point, a human being can't understand what those features are. That is a problem. So you can understand, visualize what CNN filters are looking at only in the first few layers, beyond which it's really hard. But at least we get an idea as to what is happening, what are the features that are what is it that is this particular convolution or CNN is looking at every time step, at every layer. So this is a very good insight. So there's an entire field called as explainable AI. If people who are interested, this field entirely discusses about how the model or where the model is looking at when it is making predictions, like why is it that it is saying a car and not a truck, what is that reasoning behind it, they're trying to identify with the help of several different algorithms like causal learning and everything. So people who are interested can look into that field called explainable AI. Okay. So this is what a typical CNN looks, and this is what it learns basically. This is after training. If you look at it without training, right, it will be some random values because, as you know, the weights are randomly initialized. Now let's look at okay. First, let's look at different types of convolution, and let's look at the training. So a bunch of different types of convolutions are possible. A simple convolution is what we saw, where you have a filter placed on top of the image, and this local filter, you do element-wise summation and addition, and you get the output. Simple convolution. Then there is something called as dilated convolution, where now your previous local patch, which was Your previous local patch, which was just over here, right? This, it would have ideally seen just these values. Now you make it enlarged. You make it skip in between values. Now the same 3 cross 3 filter is now looking at a bigger patch by skipping in between values. Now, why is this needed? Because sometimes objects are present in not just a small patch, right? They're present in a bigger patch like this. So to learn more and more better features, we have this dilated convolutions. So instead of looking at a small, instead of having 9 weight values to look at this particular small local patch, you use the same 9 values to look at a much bigger field of view, to have a much bigger field of view, because ideally this bigger field of view would need 25 weight values, because a 5 cross 5 will look at that. But now you've reduced this complexity from 25, you're going to 9, but at the same time you're able to look at a bigger field of view. So this is the advantage of using a dilated convolution. Okay, now let's go to another type of convolution called as deconvolution or transpose convolution. Again, the word deconvolution might be misleading with your signal processing literature, but people, this has nothing to do with that part at all. So we, in deep learning, people just use transpose convolution. So what does transpose convolution say? It means from your smaller input size. So previously, what did convolution do? You had your input, then you do convolution, then you have your output. Your input is, let's say, uh, w comma h size. After convolution, it reduces, let's say, w by 2 comma height by 2. Now transpose convolution is just the opposite of it. So it starts off with a smaller size. It starts off with w by 2 comma h by 2 and goes to a bigger size, w comma h. So that's what is happening over here. How does it happen? Obviously, there is some math behind it, which is a bit more intensive and which is beyond the scope of it, this class also. But this is what we do. This is what the idea of transpose convolution. You just try to project from smaller image size to a higher image size. If people are familiar with upsampling, this is what upsampling and downsampling means. Downsampling is when you do your normal convolution. Upsampling is when you do your transpose convolution. Apart from this, there are two other popular convolutions called spatial separable and depth-wise separable. Don't worry if these are all very new and all. I just wanted to include everything that is out there which is still popular, so that you'll at least hear the name of it. If you're interested, you'll obviously you can Google it. Nowadays, you have a bunch of resources available. But I just want you to be familiar with all these terms which are being used in today's world. That's the entire goal of today's class. So there is something called as spatial separable convolution. So let's look at the image itself. On the top, you see a simple convolution, which you have your input image, your output image, and this is the convolution 3 cross 3. Spatial separable says that. So this is kind of tedious again. Why is it tedious? Because you have to do each element wise multiplication and all for every local patch. So it's a lot of computational inefficient. Instead, what if you split this particular matrix in two different matrices? So people familiar with linear algebra, you know that you can split a matrix M with the help of SVD SPD decomposition, right? Singular value decomposition into if, for example, if this particular matrix had a singular value, only one non-zero singular value, then you can write this matrix equals to sigma into u into v. Don't worry if you're not familiar, but just imagine u and v transpose. Just imagine u and v transpose to be two different vectors. So this entire matrix can be decomposed into an outer product of these two vectors with some coefficient sigma. Again, not all matrix can be decomposable. So that is the drawback of spatial separable convolutions. Only certain type of matrices can be decomposed. So only certain type of weight values will be learned when you use this type of a convolution. So once you have these two vectors, you just multiply this. First you do convolution with this u vector, then you do a convolution with this v transpose vector. So that's it. Then you get the same similar type of an output which you got from the previous case. So this is the advantage of using that lesser computations, but at the same time, not every matrix can be decomposable. Then there is something called as depth-wise convolution. So what is the depth-wise convolution doing? Let's look at the first simple what simple convolution does on the top. So simple convolution, if you have three channels, right, in the input, The simple convolution multiplies, take that filter. Let's say this is my filter. Let's use a different color. This is my filter. So you apply the filter on the first channel, you apply the filter on the second channel, you apply the filter on the third channel. So in this way, you get the output. This is the output from the first channel, second channel, third channel. Then you sum up all these values together. That's how you do normal convolution. Depth-wise says, instead what you do, you have those three channels, you multiply, you just take a simple convolution, 1 cross 1 with three channels, then you sum up all them together into this one value. And I'll just remove this part. Yeah. So after you get this, it says that first you get the step one done. These values, then you do 1 cross 1, and then you do summation, and that will be your final output. So depth-wise convolution, again, it is used for reducing the computations. There's a math behind how it is reduce the computations, like basically lesser number of parameters, because instead of applying this 3 by 3 convolution on the entire thing, there are more number of parameters out there. You're breaking it down with two simple 1 cross 1 convolutions. So that is why your number of operations or parameter multiplications reduces. Okay. Now let's talk about the learning itself. Learning remains the same, which we did last week. Sorry, not last week, sorry, which we did yesterday for multi-layer perceptron. What were the three steps important in multi-layer perceptron, which if you remember? The first is your forward pass. Then you have your error calculation in step 2. The last step is your error backpropagation. So even for CNN, it's still the same, because here also you have weight values, this W1, W2, W3. The only difference is these weights are now in terms of matrices. Previously, you just had a single weight value, right? But now you have matrices. Each of this matrix element you can consider as a weight. Okay. So the idea of calculating partial derivatives with respect to each input or hidden layer weight still exists. Still you do that. You still multiply, you calculate the gradient of the loss and multiply with those partial derivatives to update the weights of these inner hidden layer parameters. Everything still remains the same. But how do you do that in terms of matrix? That is a bit more involved, which is clearly out of the scope of this particular lecture. But please look at the code which link which I've kept on the bottom. Yeah, please look at this link and also the next link. These two links will help you understand the math behind it for people who are interested. But don't worry if you don't understand the math also, because like I said, you saw yesterday how we did backpropagation for multi-layer perceptron in code, right? It was just 3 lines. You have to do zero gradient, you have to do dot backwards, you have to do dot step. So if you don't want to get involved behind the math, you can just still have an idea about what is happening and just move ahead and just code up the CNN. Don't worry about that. Similarly, for max pooling also, there is a back propagation that exists, because here there is no weights, right? If you remember, max pooling is, there's no weights for max pooling. It's just identifying the max value out of this small patch. So here, what you get is you get the gradients from the next layer, from the next layer to this. Like what I mean is, okay. So if I have some convolution layer over here, and this is my max pool layer, and this is my previous convolution layer, let's call 0. So forward pass, you send the values like this, you get some out, you keep on sending. Is there a doubt? Yeah, is there a doubt? Okay. Yeah. So you calculate the, in the forward pass, the values go on the top like I shown. Then somehow you, where at the end you finally calculate loss. Then you start getting the gradients back. So when you get the gradients from for C1, you send that as an input, which is these particular values. And then these particular values, you keep, when you're doing max pooling, right, you keep a track which particular pixel location did you pick that max value. So as you can see, if you look at here, this was 1.2 was the maximum, 0.8 was maximum. So those are the locations where you pick the max value. So when you're getting the gradients, you place those gradient values in those locations itself. So 0.5 will go here, 1.3 will come here, 0.4 will go here, 0.1 will come here. So you place these gradient values at those locations, remaining all you keep 0. That's it. So back propagation for pooling layers are very simple. For max pooling, at least. Average, again, it will be a little bit slightly complicated. I wanted to just show that back propagation happens even for pooling layer, which doesn't have weights or partial derivative calculations. Okay, now let's talk about some of the popular CNN methods that are out there, because what I showed is very simple CNN layers, right? Like 3, 4 CNN layers. But in reality, you have models which are having 100 layers also in today's world. 100 is again a small number, if I would say. There's 150 layer model. This ResNet model, which you see on the screen, there are three versions of ResNet. I think four versions: ResNet 18, ResNet 34, ResNet 50, and then there is ResNet 100. I think there is ResNet 150 also. So the number is basically number of layers. So the deeper you go, the more basically deep learning, again I forgot to tell you this yesterday, deep learning came because you have deeper and deeper layers in your network. That's why people said, okay, let's call it deep learning. That is the reason behind why deep learning word came. So yeah, CNNs also can go very deep when you're creating the network, but there is a problem. What happens? So like let's just simply see the intuition behind it. So when, let's just say, this particular network has some 150 layers, okay, which is very big, very deep. So what happens is, in your forward pass, you send all your values in a straight line, in I mean layer to layer. Now when you're doing the backward pass, what do you send? Like I said, gradients. Gradients is something you're sending. Now, when you're sending those gradients, gradients are what? Gradients are values somewhere between 0 to 1. It's not beyond 1 actually. It's very small values. And each gradient value will be multiplied with another smaller gradient values. So the values keep on decreasing, decreasing, decreasing to certain extent that the values become so close to 0 that all of the values after this, the gradients will be 0. Now, this is a problem because the entire network, right? The entire weight update rule, if you remember what was the weight update rule? The weight update rule was Wi in the next iteration, I plus 1 is equals to Wi minus alpha learning rate into the gradient. This was the weight update rule. Now, if gradient becomes 0, there is no update in the weight. Your Wi is equals to Wi plus 1. What are we trying to tell the model over here? That whatever weights you have, you're doing perfect. You don't update those weights. Your weights are correct. But that is not the case. Obviously, it will not be the case, especially when you start the training of the model, right? So the problem over here is the values of gradients become so small that for deeper layers, this gradient beyond a certain level becomes 0. This is called the vanishing gradient problem. So very important. I'll write it down. So this is a very popular term called vanishing gradient problem. When the gradient after a certain number of layers becomes 0, and your layers which receives the gradient 0 will not update its weight, even though you actually have a gradient and even though the model is not performing good. So to tackle this, people came up with this simple idea. ResNet model came up with a simple idea. Why don't you have something called a skip connection, which you see over here, which you look at this figure? What is a skip connection? If this is layer 1 and layer 2, so when you're sending the in the forward pass, you send the data like this from this layer to this layer to this, but at the same time you do a skip connection. It means you add the values from the two layers behind it to the output of the two layers after it. Why is this helpful? Because when the gradient now comes, let's say the gradient is coming like this, it travels as usual layer to layer. But if in this case the gradient would have actually become 0, but with the help of skip connection, the gradient again jumps back whatever value was over here, right? This gradient value will jump back and give this that gradient value. So now, if you don't use skip connection, gradient would have become 0. But with the help of skip connections, the gradient now becomes non-zero. So this was a very simple idea which they used, just a simple addition or addition values which they did, and they were able to calculate the gradients and make the entire model train. So this helped the model go more deeper and was able to learn and do much better classification and other tasks. So is this clear? I think the idea is very simple, but I think if you understood this, congratulations. This is one of the state of the art models which are people still use. Even I use in my research this model along with some obvious extensions to this. But this is how a simple CNN can work in real world. So most of the architecture novelties, right, it comes in with simple ideas like these. So you have to identify where the model is failing and you come up with simple ideas, like just an addition between the layers help them actually solve a lot of problems. Now obviously after ResNet, people went and tried a bunch of different things. Why just addition? Why not concatenate? So concatenation is basically when you're appending the values, right? You people said why not do channel concatenation? So this is the inception net by Google. So these people went way more complicated than ResNet, and they said, okay, let's have a bunch of different convolutions. So this is called as a typical inception module. So there are a lot of previous CNN layers and there are a lot of next CNN layers, but this particular operation is the inception module, where they have three different types of 1 cross 1 convolutions and a max pool. And then after this 1 cross 1, there is a 5 cross 5 and 3 cross 3 convolution. And all of these values, you concatenate them in the channel dimension. So why is this helpful? Because with different levels of convolution filters, right, you observe a different types of features, because obviously the size of the filter defines how much field of view you have, right? You can only learn certain features in a certain field of view. By having these varied type of field of views along with pooling, they were able to capture a much richer features and concatenated all those features across the channels. So the downside of this is, again, these are big models, heavy models. They need much more time to train, but obviously they are very good at accuracy. Similarly, DenseNet went even further than ResNet. They said, why just stop at having some random skip connections after a few layers? Why not have a connection after every layer? So in the dense block, let's say we have 5 convolution layers. Each convolution input will be connected to the output of the next one. This also will be connected to output of the purple one. The red ones will also be connected to the output of yellow, and so on. Again, green will also connect to purple, yellow, and orange. So on, so on. So as you can see, people just kept on piling up on that idea of ResNet and just kept on concatenating. Again, you don't have to always jump to any of these models. You can start off with ResNet, which is a very good starting point. You can see how your particular task accuracy is coming with the help of ResNet, and based on that, you can keep on changing. Okay, so I think this is what I wanted to discuss for convolution neural networks. So, and let's do a quick recap of what all did we learn, and then I'll talk a bunch of different things that you can look from now onwards, like where to go, what to do next, right? So I'll explain a bunch of different things that you can do. So before going there, I just wanted to recap. We had a bunch of different classification algorithms in machine learning, which we first discussed, which are all in these yellow color. Then what you see in this magenta color is the regression algorithms, SVR, linear, non-linear, even decision trees can do that. Then we talked unsupervised learning, and then we again talked about ensemble methods, perceptron, multi-layer perceptron, convolution. All of these can do, the 9, 10 level can do even the regression. Sorry, 9 and 11 can do even regression. 10 and 12 can do only classification. Okay, so this is how these were all the algorithms. Now let's look at the different areas in deep learning. Okay, before going there, any doubts? Sorry, I didn't pause for doubts. Any doubts or anything that is unclear in convolution? Okay, great. So let's now look at the different popular areas. By again, in no ways this is exhaustive set, because I don't think people can make exhaustive application set in today's world, because AI is and deep learning is literally being used everywhere, even in the most bizarre scenarios people are using deep learning for. So, but these are the most popular areas, I would say, or directions for you to look at. One is the computer vision. What is computer vision? Computer vision is, like the name suggests, it is an area where you try to help a machine look and perceive the things around it with the help of cameras or with the help of other sensors like lidar, radar, whatever be your sensor. With the help of this information, you make the machine look at what is its environment. Usually the typical input is your standard RGB images with the help of camera, but that's not the only thing. If you remember, in the starting autonomous driving, we used a bunch of lidars in that, radars in that. So you used a lot of other sensors. Then comes natural language processing. So as the name suggests, this field is basically trying to make a machine understand human language. So they try to make a machine read, write, not understand big documents, summarize documents, a bunch of different tasks which we will discuss. So all of them deal with some input of human text, language in the form of text, basically. So it also not just deals with any one language, not just English. They deal nowadays. There's something called as Indie LLM. I don't know if people are aware of it. So this was what do you say, an initiative taken by the Indian government to come up with a LLM model that can be like a chat GPT for Indian languages. I think Indic LLM or something the name is called. Look at it. One of my professors from IIT Hyderabad is also a part of this project. So their work is actually interesting. If you can contribute, do definitely contribute, because they need a lot of researchers and engineers at any point of time. So apart from that, there is something called as speech recognition and generation task. So this is where where you make a machine listen to the human speech and understand what it is trying to say, and at the same time talk to human beings in their own human speech. So this is that area. So now let's go into computer vision itself. So computer vision, like I say, it is basically trying to understand your environment around you. So like the image says, what do you need to understand? You need to understand the entities, like, okay, this is a dog, this is a person, this is a traffic light, this is entire thing is a road. So you need to first also understand how these entities interact with each other. Car goes very fast and car is non-living. Human being walks relatively slower and their life is more precious. A bunch of different these relations need to be learned. So for that reason, people divided this computer vision field to have several different tasks. So these are most of the popular tasks. Apart from that, there are few other which are possible and which people work on, but these are most popular ones. So these are the 8 different tasks. We'll go with each task one by one. So, what is image classification? Image classification is what we've been discussing all along, where you have an image, let's just say this image of a cat, and you give a label to it called cat. Object detection is slightly different, because in image classifications, most of the times only one particular object is present in the image, which is a simple image classification task. In object detection, you'll have multiple objects, and also you need to draw a bounding box across each of these objects. So this is your object detection task. Now, what will be the output? Output will be a bounding box across the dog class and say this is dog. Then across this cat class, say cat. Similarly, another cat class, say cat. Then there is a small duck. You draw a bounding box across it and call it a duck. So this is the task of object detection, which is different from classification. Then there is something called as segmentation. There are two variations to segmentation. So let's first see the normal segmentation called semantic segmentation. What does it do? If you look, this is the input image, which is like a dining hall. And the segmentation says what is the difference between the different textures or objects that are present in my scene. So all the chairs will be one particular type of an object. All of them get a similar color, which is blue. The floor is a different entity than all the other objects, so that gets a lighter gray. Similarly, the table is a different entity than the chairs and other things, so that entire thing is again one continuous thing, so it gives white color. So you're seeing, right, what is happening. I hope you're understanding. It's basically creating different maps or segments in your entire input image and calling them as all the similar things will be given similar color. So this is called semantic segmentation. Instance segmentation is combination of semantic segmentation and object detection, where each particular, previously what, all these chairs were one color, but now I want to calculate the number of instances of all these chair also. So each chair will get a different color. So this is what instance segmentation do. It is a more harder task than semantic segmentation, where not just segment all the same objects, but at the same time identify the instances that are present for each object. For the same object, how many instances are present? Like all the chairs, you can now count how many chairs are there. Previously, you couldn't count how many chairs are there. So depending on your application, you can choose whichever task you want. Okay, so this is a difference between all these four tasks. First one is image classification. Second one is semantics. Bottom one is object detection. Then on this on this top right, you have semantic segmentation. On the bottom right, you have instance segmentation. Then there's something called as object tracking. So a difference between object detection and object tracking is, in object detection, you just form a particular bonding box across the object and you forget about it. You don't relate. But in real world scenarios, that is not the case. Like for example, let's look at this car, right? Car or truck. This is coming somewhere from the back and it will keep on going. Sorry, this is coming somewhere from the back and it will keep on coming front. So you have to keep track of all these objects in the entire video frame they are. So where did it start, and then the same box is traveling towards the end of it. You should not get confused that this particular car which is at the front is different from the car when it started from the back. These are the same cars when it starts from the back. So this tracking is very important. One in what is an interesting application was object tracking was used during COVID time. I think it was Andrew Ng's lab that created an algorithm which kept track of how people were moving in markets and how many people were interacting with each other or how close they were, and then they were able to make more and more announcements that please maintain distance, social distance and all. So it was very popularly used object tracking to keep track of people's movements in the market and tell that okay, these people are not maintaining social distance, please maintain social distance and all. Not just that, even for real autonomous vehicles people use object tracking. Then there is something called as pose estimation. Like you can see from the image, pose estimation is where you have a particular human being in a particular pose and you try to map that pose with the help of the skeletal graph. Where is this needed? Again, you can use this to identify the movements of bunch of players, right? In sports analytics you all see cricket and football and all. So to understand how the movements of the people are and what will be the next step of action that we will take, for that you can understand pose estimation. Or not just that, even for like for people who are trying to do gym or do some rehabilitation of getting back in their own physical movement and all, you can keep track of their pose estimation and tell okay, this is where you're doing wrong, you can improve your pose like this, do more better lifting of weights with this particular angle change and all. A bunch of different applications are possible with the help of pose estimation. Then there is something called as image generation, which is very interesting because I think nowadays you people must have heard of this DAL-E algorithm and a bunch of diffusion model algorithms. So these are all image generation task based algorithms. So like the name suggests, you try to generate images with the help of simple prompts. It's not just prompts also. Sometimes you can give two images, like on the top, if you see, you can make zebras into horses like this, which you see on the, and from horse to zebra. So these things also can be done. You can either give a prompt or you can either ask them to take zebras from one image and make them horses in the same different background. So bunch of these things are possible. Image generation, where do people use it? If you use these photo editing softwares, right, people use image generations over there. And image generation is in general used for creating content also nowadays. So a lot of different applications are possible. And then another very realistic or very interesting task is scene reconstruction. So if I have a simple RGB image, so RGB image doesn't have depth. I hope you all are familiar. Image is just a two dimension, so we don't have a depth perception. So but in reality they have some depth, right? Like these images, when they were captured in real world, they have some distances between them. So that is what scene reconstruction tries to do. It creates that entire scene that is present from just a simple 2D image. So they try to create they have a bunch of different algorithms which they try to create how this originally the scene looked like. And where is this important? Your VFX, all your big movies, right? Your Bahubali and your what do you say, Kalki movie and all. They use these scene reconstructions in a certain way. Obviously now they use VFX more, but scene reconstructions can actually help with VFX a lot. They can create more realistic scenarios of this imaginary worlds with actual depth and all with the help of these algorithms. Not just in those scenarios, you have a lot many applications for scene reconstruction. Okay, so and these are again popular methods or algorithms that each of these tasks use, but these are in no way the only algorithms that are out there. There are a lot of interesting algorithms that keep on coming every 3 4 months. Please keep a look at it if you're interested in any of these tasks. But these are some popular ones. You can start off reading if you're interested in any of the tasks with these algorithms, and you can start from there. Okay, now let's move on to the second important field, natural language processing, where your tasks are something like these: your text classification, where if you remember in this, if you're in the start, I was telling if you're given an input text and you have to classify whether it's a positive class or a negative class based on the movie review. So that is kind of like a text classification. Then there is question and answering, which I think most of you are familiar. You give an input image, not just image, you can just give a text in form of a question, and you ask for an answer for it. Then there is machine translation, which translates from one language to another. Then there is summarization, which give a big paragraph or like a big report, and the model should able to summarize all the important points. Then your popular chatbots basically interact with it like you interact with any normal human being. So I think these examples are the same. Basically, you give a document data set and you classify which does it belong to: art, business, culture, entertainment. Similarly, if you question answering is you give an entire document and you pose a question. Like in this entire document, you pose is Python dynamically typed? Now it look at this entire document, identify yes, Python is dynamically typed. So answer will be that Python is dynamically typed. So this is the working of question and answering task. Language translation, like this particular English to Hindi. I think everyone knows this translation algorithm, like what translation means. Then summarization, right? Like I said, you have this entire paragraph and then you can summarize. So there are different types of summarizations that are possible. One type of summarization is you pick important statements verbatim as it is from the document. Then there is something called as paraphrasing, where you understand what is the important points that are being said and you write it in your own words. So you can use, there are a bunch of different summarization techniques that can be used. Chat GPT, chatbots, I think I don't have to explain what these are. Everyone knows and everyone uses. If you don't, please use Chat GPT because it's very helpful to do a lot of your day to day tasks. Okay, now these are again popular algorithms that people use for these particular tasks. I think LSTM BERTs are still used for classification, but nowadays people use transformers for most of the things. So I'm your LLMs, right? Your large language models, your Chat GPT, all of them are transformer model based. So they I think transformers kind of became the go-to model right now in today's world for most of your algorithms. Even CNNs are instead of CNNs, people are trying to combine CNNs along with transformers instead of only CNNs for even dealing with images, not just text. So transformers is kind of very important. So that is why I wanted to maybe give you a brief introduction to transformers, because I think it would be unfair if I don't talk about it when I'm talking about popular trends and algorithms, because everywhere you go you see transformers today. So let's briefly discuss. Transformers in itself is a very big lecture, but I'll try to keep it very simple. Please do look again at the links. They are very well explained with all images and flow chart and everything. Look at the links which I mentioned in these slides on your own time to understand what transformers are. But let's see. So a transformer is nothing but it has two things. It has an encoder, which is this particular left side, and it has a decoder, which is on this right side. So what does encoder do? Like the name suggests, it takes your input text and it encodes in some what is this smaller subspace, in some local representation space. It encodes all these text, assuming that that particular representation is very optimal. And then in the decoding phase, you take that representations, encoded representations, and give it as an input to decoder, and it will decode and give output based on your task. Like for example, if your task is machine translation, you give input text in English. That English is somehow represented in some subspace, and that encoded subspace of those English words are given input to the decoder, and the decoder outputs in Hindi. So the main component that made transformers popular is this multi-head attention. So you can see in orange color blocks, right, multi-head attentions that are present. That is what made transformers very popular. So this entire network doesn't use any other RNNs or all. RNNs are predecessors to attention. It doesn't use any of those. It just uses multi-head attention. And in that multi-head attention also, the important operation is a scaled dot product attention. It's a very simple idea. It's basically doing a dot product. Like the name suggests, it's a scaled version of a dot product, nothing else. You just do dot product between few vectors, and that's it. That's what the entire your chat GPT, llama models, all large language models, all of them work on this simple dot product at mechanism. So such a small idea, but the way the people used it and the way people are modifying it in today's world, it's just interesting to see. But let's discuss a bit more about it. What does it attention do? So let's assume this is the sentence you have: extreme brightness of the sun hurts the eyes. So for a human being, you can understand a lot of things without you actually putting effort also, you'll immediately understand. When I say extreme brightness of the sun, when I say the of the sun hurts the eye, this the and all, what is it closely associated? This the is closely associated with the sun. This the is closely associated with the eyes. It's not like this particular the is associated with eyes, because there's a relationship, right? So these type of relationships which you learn to or attend to is what attention tries to learn. So you have to, when you're focusing on this word the, which words, other words should I pay attention to? That is what the entire concept of attention comes. So if you look at this, if you have the same words, extreme brightness of the sun hurts the eye, extreme brightness of the sun hurts the eye. When I'm looking at the word the, attention model after training says focus on the sun more when you're talking about this the. But when I'm talking about this the, it says okay, maybe focus more on the eyes, little bit on the hurt also. So this is where you're training your model to identify or training your model to focus on certain things when your inputs are of certain words. So this is what attention or the name word attention comes from. How does it happen? Like I said, it's with the help of these simple scale dot product. So I won't go into all these calculations in detail. Like I said, look at the link. It is very simple. But all the scale, what do you say? All the scale dot product attention do is this. So there are three vectors which we have: query, key, and value. So these vectors represent different things. Your query is like what is your input word, or which is like the input, right? Like for example, here the word is the that will be your query, and then key and value is basically what different representations of all the possible other words which you should attend to. So it's a dot product between query and key. You calculate the softmax and you multiply with the value vector, and then this is the output Z. So this simple calculation is what is called as a scale dot product attention. You do this multiple times to in your multi-head attention, and you combine that multi-head attention multiple times in your transformer architecture, and that's it. You are ready with your powerful LLMs. So this is a very simple form. Obviously, LLMs have more different slightly variations to this transformers, but the idea is the same. So just look into this link and you'll understand more clearly what, because this requires a little bit of understanding of NLP, how the words are encoded and all. That is beyond the scope of this particular course. So like I said, even attention is being used in CNNs, which is very interesting to see, because attentions just started off for text, but like I said, attentions are now everywhere. How do they use in CNNs? You take a convolution feature map, and then you do different types of convolutions for three different matrices: f of x, g of x, h of x. Just like you had your QKV, right, in the normal transformers or attention. Here this FGH acts like your QKV. Then you do what you do first. You first do a dot product between f and g, take the softmax, and then you multiply it with uh, h, and then you get your v value, and that is your final output. That the z value is your final output. So this is a simple type of basically how an attention can be used in CNNs. So why can CNNs benefit from attention? So if you remember, what does CNN wants? It wants that local dependency, right? So in a particular image, if you're looking at like, let me just show that. So if I have this image, and let's just say if I have a boy and he's playing with a frisbee. So now if I pose a question to this particular image, like in a question and answering task, if I give this image and ask who's playing with the frisbee. So what the model will do, it will focus on this local part, this convolution features, it will focus on this. Now when you're focusing on this, what after the training of the model, the attention will be mostly on this person. The attention model will say, whenever you're focusing on frisbee, focus on the man, because they have a very close relation. So this is how the attention helps in CNNs. So now immediately when I pose a question, who's playing with the frisbee, it will look at frisbee, and the attention values it will look, which is mostly high with the man, and it will reply with an answer that the man is playing with the frisbee. So this is a simple use case of how attentions work for CNNs. There are a lot many which you can explore on your own. Okay, now let's go a little bit about a different direction, which is your speech recognition and generation. Let's look at the tasks itself. So basic task, automatic speech recognition, where you have a voice input and then your model should identify what is being said. Let's say, like, if someone is just saying hello, and the model should take that voice sample and it should predict the word hello. That's a simple speech recognition task. So your Alexa, your Google, Siri, all of these are some type of speech recognition systems only. Then there is something called a speaker identification and verification. So let's talk about identification. So identification is whenever a person is saying something, you need to first identify whose voice is this, that is a particular voice, and then verify it, is this actually that person's voice or not. So there are two different things. Identification is you're identifying whose voice is it. Verifying is this voice, is this Bob's voice. That's what we have to verify. Again, when you if you know that when you say okay Google or hey Siri, for that reason, only the person whose voice is registered or verified in the phone, right, that can say hey Siri, then only activate. Only that particular person, when he says hey Siri, gets activated. Siri gets activated. So that is somehow using these identification and verification systems. Then there is text to speech. So you have a lot of apps online where you can just type in a bunch of text, and then your automatic text to speech algorithms will give output in a very robotic voice. So it'll just read what you wrote. So that is nothing but your text to speech generation. Obviously, there are a bunch of new all these chat GPT models, right? GPT 4o can do this. It can talk to you also very nicely. Then very interesting application is vocal emotional recognition. So when you talk to a particular robot, it should identify what type of emotion you are currently dealing with. So you can either be sad, happy, angry, like you can see on these. So this is very interesting application because nowadays, I don't know if you are aware with the news, in mostly in China and Japan and even in South Korea, the people are feeling more and more lonely and depressed and sad. So people are trying to come up with more of these bots, either in the form of chat or bots which can talk to you and identify what type of an emotion you are currently in, and how you can make the person feel better. Kind of like a support, a friend, like a friend basically. So a lot of applications are being currently researched for this type of bots. Then there is speech to speech translation also. Again, your Google does this very nicely. So you can talk in one language and the output will be again in speech in another language. So these are a bunch of different algorithms that are there. You can always check that out. Again, there are a lot of LLMs also playing in this today's world with for these tasks also. You can also check them out. Apart from just individually having these three fields, there's something called as multimodal deep learning. And this is where people say that it is going to change the industry in the next 10 years. Because right now, up till now, progress has been done more or less, exponentially, either in computer vision or NLP or speech recognition separately. But multimodal is still in a very young stage, I would say, in research. So recently, I think few months ago or a year ago, I've heard that Google invested, they created a big team for multimodal deep learning. Not just Google, a bunch of different companies have invested a lot in this area of multimodal deep learning. So in the next few years, you might probably come hear this word a lot, multimodal deep learning. If you already did, then great. So what does multimodal deep learning say? So it basically combines a bunch of these different inputs, and your tasks change based on those. So if I combine images and text as an input, my bunch of different tasks come in. If I combine images and speech, a lot of new tasks come in. If I combine all these three, again a lot of tasks come in. Let's see what those look like. So these are some type of tasks. Again, there are a lot more. Like I said, the simple task is visual question answering, where you have an image, you have a text, and your output text will be a question. The output should again be in the form of a text. Your image captioning, your audio visual speech recognition, and robotics. Let's look at those. Visual question answering, like you can see, I give these images and I ask who's wearing the glasses. In the first one, it should say man, woman, and a bunch of other questions like how many children are in the bed and all those things. Then image captioning is slightly different. You give just the input as an image, and then the output the model should give in the form of a text describing what is in the image. So it should say, okay, this when you give this first image, it should say a young boy is playing basketball. Similarly, a bunch of different captions. Again, there has been a lot of research that is being currently done, but there is still a lot of scope that is there in these particular tasks. Then there is audio visual speech recognition. So previously, people just looked at the audio and then used to recognize what they're saying. Now, not just the audio signal, they also look at the mouth, the lips of the person, mouth localization, the eye tracking, and everything. And then they exactly say, okay, what is that exact word that the person is saying? Very powerful task. Then there is something called as embodied AI. I think this will be very interesting for many people because this is something which people have always dreamt of when they say AI, right? So what do you need an AI for? If you tell if you tell the particular robot to do a task, it should do your task. So that is what kind of embodied AI says. So embodied AI has all the senses that is available most of the times, like your camera, lidar, radar, and it deals with all type of inputs, your images, your text, and your speech. And then if you ask it to say, okay, what is the color of the car? Let's say it is inside the living room, and you ask a robot, okay, what is the color of the car? So it will first analyze, okay, where will a car be? It will be outside the house. So it then goes outside, travel outside, come to the last image where it sees the car outside, then comes back and says it's orange. So it's a very it's like a complete AI system. That's why it's called as embodied AI, where it kind of completes everything what you want from a robot. Very interesting field. It came, I think, in 2018 or 17. I don't remember clearly, but there's a lot of research that is going on in embodied AI. Then, obviously, I wanted to discuss a little bit about this popular word, large language models. And today, it is pretty much everywhere out there. No one expected it to explode so much, but I think it's there everywhere in every application, even in images, even in multimodal deep learning. Everywhere you go, there is definitely a LLM that is there, and the research is actually happening exponentially fast. Previously, people used to write papers. New papers used to come out every year or so. Now new papers on LLMs come out every 2-3 months. So you have to be very fast to keep track of the research. So what are the different tasks? It can do all the tasks which I told till now: text generation, language translation, question answering, code generation, summarization, conversational AI, and etc. etc. All the tasks which we discussed till now are more or less done in some way or the other by LLMs. Obviously, accuracy or the performance is not great, but still it is capable of doing. So as you can see, there are different types of LLMs on different levels. You have application level, where it is like your GitHub Copilot, right? So it is based on some fundamental LLM, but it is more application specific to write your code or correct your code. So like that, there are a bunch of application specific. Then there is something infrastructure specific also, infrastructure layer, where your inference is done using certain softwares. Your hardware, certain companies' hardwares are being used and softwares are being used for those hardwares. A bunch of different soft things related to LLMs itself. So a small history also I wanted to give about how these LLMs actually blew up. So this was again not a new idea, just like how perceptron was an idea back in 1969 or something. I forgot the date, 1957. So LLMs actually was not something that came out in 2020. So the initial ideas were actually somewhere in 1950s and 1980s. People tried to establish something like a big language model that can do some multiple tasks like these. Then people started again using in 1990 to 2012. Your first GPT came out, which was your generative pre-trained transformers, where people tried to come up with a model that can use some language statistics and some other statistics to generate better and better text. Then in 2018, Google introduces BERT. Then from there, it kind of opened the doors to LLMs, your large language models. So the idea is not something only after 2020. 2018 was actually kind of like a breakthrough year for these LLMs where BERT came out. 2020 is remembered extensively because that is where OpenAI released GPT-3, which kind of was very accessible to a lot of people, which made it more into our day-to-day lives. But the idea itself was way back. And then I think in today's world, you have so many LLMs. So people kind of look LLMs in these variety of metrics, I would say. Like it needs to be logically correct, it needs to be logically robust, it should be harmless, it should be conciseness, readability, metacognition, completeness. All of these means like all of these have their own definitions and everything. Some of them are also not very like quantitative, it's very qualitative. But we want an LLM to kind of do good at all these particular metrics. And then I think these are all the language sizes. Again, this is only till March 2023. It's been almost a year. And in fact, I think it was 3 days ago when GPT released a new model called as GPT OI or something. I forgot the full form, IO or something, where it was able to do complex mathematical reasoning. So do check it out if you are using GPT. It's people have mixed opinions about it, but nevertheless, it at least is better as what I heard than previous GPT versions. So these are all different models. And like I said, if you look at the parameters, right, like 52.4 billion, 175 billion, 530 billion. So up till now, what we discussed in multi-layer perceptron and CNN set were small, very small parameters in million parameters. These are all in billion parameters. So it's a lot big models. These are very big models. Okay. So this is what I wanted to discuss. If there is any doubt in anything which you want to talk more on everything, we can discuss now. Otherwise, I'll just show you the code for CNN and we can end the session with that. Any doubts or anything that you want to know about more, or anything which new keyword that you heard about, you want to know what that keyword is? Okay, so let's just quickly discuss the code for CNN itself and then we can end the session. Okay, so as usual, I just wanted to first show what the convolution operation, how you can do a convolution operation using NumPy. But don't worry, you don't have to do this from scratch. PyTorch does it for you. But for understanding perspective, I think it's interesting if you can do this. So it's simple input matrix. You give kernel matrix and you just write two double for loops where you place this kernel on this patch, image patch, and you keep on moving one place to the right, and you just do that element wise summation and multiplication. Very simple code for convolution, not much. Just look into this code. I won't go in detail because the time is less a bit. Let's look at the actual important part which I wanted to discuss. That is the creating a CNN network, a convolution neural network with the help of PyTorch. So today we'll learn few important classes or modules in PyTorch called datasets, data loaders, and transforms, which are very important for you to do whenever you're dealing with images dataset. So let's look at them. So as usual, you import all your necessary libraries, torch vision. Then there is this new module transforms. NN is what we used yesterday also, which is a neural network module. Then there is functional, which we'll again discuss, and optim, which is nothing but optimizer, which has all the optimizers present. Okay, so a transforms. Let's come to the first. Is there a question? Okay. So transforms is used for making some operations on your input image. Now, what do I mean by that? You take a simple input image like a cat and dog. Now, usually what people say is key, you can also make some augmentations to this image and send that as an input. Why? Because creating augmentations will usually create diversity in your data set. The more the augmentations, the diverse your data set, right? And like I said, the data set which you usually use or collect, right? That is in no way complete when compared to the entire data set that is out there. So for that reason, people do some augmentations on your input data set. That is where your transforms come in. So what are these augmentations that look like? You can either reduce the intensity of the image, you can slightly rotate the image, you can slightly add noise in the image, you can make the image black and white, or a bunch of different operations. All those particular operations, right, which are just described, color change, intensity change, or rotation, flipping, all those are existing in transforms library. Do check it out. So this is how you create that particular transformation. You call transforms.compose. It will basically compile all the transformations you want to do. Here I'm just not doing anything. I'm just converting first my input image to tensor and I'm normalizing the image. So from 0 to 255 pixel values, I'm just normalizing to 0 to 1. Also, one other important thing, always convert your input images, right, to tensor, because PyTorch takes the neural network models built by PyTorch takes input only the tensors, and by default your images won't be in tensor format. They will, I think, be in numpy array at the most, or in some other format. But it's always important that you first convert into tensors with the help of this transforms or to tensor, Then after that, you can use this as an input to your neural networks. So first you define your transformations, and then after that you load your data set. Today we will load the same CFAR10 data set which I discussed yesterday, right? So that was the a small data set which had bunch of common objects like cat, dog, and all those things. 10 different classes of each class. I think 32 cross 32 was the image size. So we load the same data set. So data set is available in Torch, PyTorch. You can access it this way: torchvision.datasets.cfar10. Here you just mention root argument says where you can download this data set into in your local system. Just mention the path. Train is equals to true. Basically, there are two splits available for CFAR10: train and test. So when you say train true, you'll only the train part will get downloaded. Download obviously you should mention as true, and then you mention what transformations that you want to do on this particular data set when downloading. So these are all the transforms which we mentioned. Here I didn't mention anything, but you can add a bunch of different transformations that you wanted to do. So with the help of this, now you load the data set in something called as a data structure. So you know structures, right? In programming languages, data types or data structures, right? Data structures are what? Like array is a data structure. Similarly, tensor is a data structure. So in PyTorch, your data set loads in a data structure called datasets. So that is the word of the data structure, dataset. So whenever you're loading any images or any dataset, right, that particular images or dataset is loaded in this structure called dataset, which is your train set, what you created right now. So this train set contains all the images which you want from your data set. But here we can't still use this because you have to first convert them into a data loader. I'll tell you what it is. In the next line, we are creating a data loader. Data loader is where you create your batches for your data set. If you remember yesterday, we talked about why batches are important, because you can't load the entire data set because the limitations of your GPU RAM, right? So you only load a part of the data set, which is your batch. So this is where you create those batches with the help of data loaders. You data loaders takes the following inputs. It takes your data set, which is your train set. You mention what should be the batch size. Like I said, a lot of different variety of batch sizes are available or possible. Here I'm taking 4 because it depends on how big your data set size is. And then there is something called a shuffle is equals to true. This is a very key important thing whenever you're at least creating your train data loader. Why? When shuffle is equals to true, it creates, like the name says, it basically shuffles your entire data set before creating batches. And with the help of this, the model won't see a similar class, because when you're initially loading the data set, all cats will load together, all dogs will load together, all the other classes will load together. Now, when you send in a batch, let's say batch size 4, if all the 4 samples belong to cat, the model is just seeing cat at like for the first 10 batches. It's not learning the diversity in classes, right? It is just learning that, okay, maybe there is only one class in this data set and I'm doing good at it. It's only cat. But suddenly after 10 batches, you send a dog. Now the model is confused. The model is like, okay, I never saw a dog till now, so it never updated the weights for dog. But suddenly it sees a dog, then it again starts learning from scratch. So that will be a big problematic way of training, because the it never converges. You keep on showing new classes after a certain set of batches. So to avoid all those things, best option is shuffle the data set. So with the help of that, you try to bring in as many classes as possible in your each batch. So that is why shuffle is equals to true is very important. Then similarly, you create one for test also. First, you create your test set. Then you create a test loader. You don't have to shuffle test loader because you're just predicting on it. It doesn't matter. So you don't have to shuffle them. So here, these are just classes that it's written just for you to know what are the different classes. This is where you create your convolution network. Very similar to how you created your multi-layer perceptron. It is nothing but you first define your class and then you inherit this parent class nn.module. If you remember, I told that this is very important. This basically tells PyTorch that this particular class which you created is of the type neural network. So make sure you always inherit nn.module for this network, for your any neural network class. Then I said two important functions you need to define: init function and forward function. In init function, you define all your important global variables, like what are the different convolution layers, pooling layers, your fully connected layers. All of them are defined in init. Like you can see here, right? I defined convolution 1, conv 2D. And what are these numbers? The first number says what is my input channels. Initially, this is the first convolution, so input is RGB, so number of channels will be 3. What should be my kernel size? And no, what should be my output channels, which is the middle term? What should be my kernel size is the last term. So these are the three values that are usually sent as an input to a convolution. You don't have to write anything. You just write this and your convolution operation will be done automatically. Next, you define your pooling. Pooling also, you basically have two values. You mention what is the pooling filter size and what should be the stride value. So it's both 2 and 2. Similarly, for the next convolution, you again define 6 is my input because input channel size. That is because your output channel size of the first convolution was 6. Then your output channels is 16 after the second convolution, and the filter size is 5. Now for linear, you see the values are 16 into 5 into 5. This is because you're flattening the vector. I'll show you how you're flattening. You flatten the vector, and that is why your input to this particular linear layer is that flattened vector size. And then you have the output all the same, which we saw yesterday for multi-layer perceptron. Now let's look at the forward function. What did the forward function do? It basically tells the network how the data should flow from one input layer to the output layer. So this is X is the input data. It first goes into convolution 1, then it goes into ReLU activation, then it goes into pooling layer, then that output will now go into second convolution layer. You send it to again ReLU activation, then pooling layer, and this output is now flattened. This is where you flatten. If you remember yesterday, I showed you a command dot view, which will help you to reshape your tensor, right? That is what I'm doing. With the help of dot view, I'm just making it a vector. And now with this vector will go as an input to the first fully connected layer, then again activation, then second fully connected layer, activation, and finally your output layer. And this is X is returned as your output. So if you understand on paper how the your network flow should happen, just blindly write like that in your code. So it's very important to understand how the network is created or what you're creating. Then you can easily write the code. That is because writing the code is not problem. It's just logic should make sense when you're writing the code. After that, you just create an instance of this class. And then after this particular thing, you create your loss function like same like we did yesterday. Criteria is cross entropy loss. And then you create, you use SGD optimizer here, very simple optimizer. And now you write your training loop. Yesterday, if you remember, we just wrote for epochs because I said it is a small data. But today we have big data. So you write two for loops. One is for epoch, and the inner for loop is for all the batches. So one epoch is said to be completed when the model sees all the batches in a data set. That means it completes all this inner for loop. Inner for loop is completed when all the batches, mini batches, are seen once by the model. So then we say one epoch is done. So inside this inner for loop, you first get your input and labels, input and target with the help of the train loader, which you see here, right? Train loader. Oh, sorry. With the help of this train loader, you get your input and labels. Then here you first zero out your gradients. Then you do your forward pass at this step. Then you do your loss calculation. Then you do your backward pass with dot backwards and dot step. Everything remains the same like we did yesterday. The only difference is creation of this class. That's it. Creation of the class, and now you have two for loops because the data is big. Once this is done, you just print the values. You can see all of these are losses. The loss keeps on decreasing, starts off from 2, it comes down to 1. Here you see in the brackets, the first one is the epoch number, whereas the second one is the batch. After every 2000 batches, you're printing the value. So in total, there are 12,000 batches. So it's a very big data set. So I think roughly 50,000 samples, 48,000, 12, roughly 12 into 4, 48,000 with some samples here and there. Even for epoch 2, you do the same thing. You print the values. So this is how you train your simple CNN network. Nothing much. So like any other thing, you can do the same hyperparameter tuning, which I showed you for machine learning, right? Here I want to do for 3 different classes. So CNN1 has different input channels and output channels and number of convolution layers. It has only one. CNN2 has 2 convolution layers. CNN3 has 3 convolution layers. So if I have 3 different CNN architectures, how will I pick which I want? Same for loop you can use which we used previously. So we create a function called training and validation. and this has the same train loop which we just saw. It has then after every epoch you do validation also and calculate the accuracy. Now for hyperparameter tuning, you just have this small for loop for each model, and all the three models you call the train function for each model, get the validation accuracy, and you find out which is the best one based on the validation accuracy. It's very simple. It's the same idea which we use for hyperparameter tuning for machine learning, right? Same idea. So then you get accuracy on with CNN1 so and so, so and so. The best is having two layers of CNNs, and the final best accuracy is 59.54. Okay. So this is how CNNs work. So this is you creating a CNN from scratch. But like I said, most of the times you don't have to create from scratch. All the existing big models are there. You can start off from there because they provide very good starting point for you. How do you use an existing CNN model that I wanted to show you once? So again, on the same data set, you can these are all the same things. You load the data set, you create data loaders and everything. Only difference is here. Sorry, here. So now your model is a ResNet 18 model. So you can use model.resnet. Pre-trained I kept false. So if pre-trained is false, it means the weights are randomly initialized, but the architecture is like ResNet 18. But I would suggest keep pre-trained is equals to true and see the accuracy jump. Pre-trained true is basically when you get the optimal values for which ResNet has been trained. Those values will be loaded. If pre-trained is false, random weight values will be loaded for ResNet 18. Just do that experiment and maybe you'll see the difference. Everything else remains the same. You just have to create the model, change few layers of the model like convolution 1 and fully connected layer, because you have to adapt that ResNet 18 to your data set, right? So you have to change those few layers, and everything else remains the same of calculating accuracy, for loops or for epoch and mini batches, and that's what you print. So here test accuracy is 39.5 because pre-trained is false. Use pre-trained and see it will easily jump to I think 70 or something. Okay, yeah, I think this is what I wanted to discuss in today's class, and hopefully all these sessions were very helpful and informative. Any questions or anything in any part that throughout we discuss in all these 6 days, you can ask me right now. Anything that you want to know more, or any direction or anything that you want to talk about, where you want to go next. So in my opinion, I think you have a good starting point uh, now to take more interesting deep learning courses, because you understand most of the basics in the last two classes which we discussed. So I would suggest taking one of these NPTEL courses by my Professor Vineet. He is teaching deep learning for computer vision. You can always look into his course. He's a very established researcher. I'm not sure if you're familiar with him, but his works are very acclaimed at international level. So do check out his course also. It's very interesting. He talks everything about computer vision in more detail, all these CNN architectures, everything, the object detection task and all those things. Even he talks about transformers, diffusion models, all those things. I think you can start with those courses, which will be very helpful if you want to get into these fields. Okay. So I think, ma'am, if there are no questions, I'll stop sharing my screen.
So, dear participants, any questions?
Imagine that you are No, ma'am. Asli Benjamin का क्या?
So, dear participants, you can share views or suggestions or feedback on this FDP. Okay, thank you.
Madam, Nagajyothi madam,
Yes, sir.
principal sir will be joining in a minute. Okay.
Okay, sir.
Meanwhile, you can ask the participants to give their feedback.
Feedbacks.
Okay. So at least two or three.
Two or three, any participant can give your any suggestions or how was the conduction of this FDP.
Hello,
Okay,
madam.
hello, sir.
Good evening,
Sir,
madam.
please. Sir, please.
Myself is Shankar from Naranamma Engineering College, madam.
Good evening, sir.
Good evening, ma'am. Yeah, the program is very excellent, madam, because the timing, especially timing, is very good, madam. From 7 to 8:30 is a the timing is very good, madam. And Abhin Dayal, sir, I never seen such a way we call as a teaching such kind of is a very excellent, madam. It is.
Yes, sir.
I never see. I attended many FDPs, but sir, the way of explanation is very excellent, madam. Actually, so really
Thank you, sir.
thank you,
Thank you.
Avin Dayal, sir.
Yes, sir.
Yeah, thank you,
Thank
sir.
you, ma'am.
Thank you, sir.
Thank you, ma'am. Thank you.
One more participants, please. Okay, thank you. Good evening.
Any of our students?
Any of our students, many students are joined.
Ma'am, is there any exam, madam?
Yes, sir. Tomorrow we'll share the link, sir.
Okay,
Link
tomorrow
for
is there, madam,
exam.
exam?
Yes, sir.
Okay, at what time, ma'am?
We will share in the WhatsApp group, sir.
Okay, okay, madam.
Okay, sir.
And the certificate, madam?
Certificates also after the examination, we will share the
Immediately you will
certificates,
share,
sir.
ma'am.
1 or 2 days, sir. It will take 1 or 2 days.
Okay, okay, madam. Thank you,
Okay.
ma'am.
Oh, thank you, sir. Thank you, sir. That was a great presentation, sir. Today, Abhin Dayal, sir, delivered talk on convolutional neural networks and present research scenario and directions. So that was great presentation, sir. You covered all the topic which we had proposed in the schedule. And you covered all the practical problems also. Thank you, sir. Thank you very much.
Yeah, thank you, ma'am. Thank you, everyone.
Okay, sir. Now we move on to the valedictory session. One minute, sir. The principal sir already joined. Welcome, sir. Hello. Welcome, principal sir.
Yeah, thank you very much.
Sir. Now I take the privilege to invite our guest of honor, Dr. J.V.R. Ravindra sir, Principal, Vardhaman College of Engineering. Welcome, sir. Now I request our principal sir to address the gathering.
So, Principal Sir, Mr. Abhin Dayal is there from IIT Hyderabad. He is the resource person for this 1 week faculty development program. The sessions were excellent. The sessions were excellent. Even the participants are also very happy. We should thank Dr. Praveen Kumar, IIT Hyderabad, who has introduced Abhin Dayal. Through him only we got his contact. The sessions were very good. I think we request you to give the concluding remarks about the workshop, sir. This FDP. Thank you, sir.
Okay, so first of all, thank you for this opportunity for inviting me as guest of honor for this valedictory function, and I would also say thanks to Dr. Avin Dayal from IIT Hyderabad, and Abhinav also. I'm very close to, close to in the sense there are lots of research I do with IIT Hyderabad. Probably, I haven't seen you there, but next time when I come to the lab, probably, definitely I come and see you. And we
Oh,
work with,
yes, Professor, definitely.
yeah, so we work with Professor Jafar as well as, Sri Ram Murthy Garu. And
Okay, yeah,
yeah, so I mean, like, when I was doing my PhD in Triple IT Hyderabad, they were used to work in Professor Egna Under Egna they used to work in the signal processing lab. So it was
yes.
yeah, it was I mean, it's a good to always work with them. So thank you very much, sir, for your wonderful guidance as well as support to the, audience as well as Vardhaman students and Vardhaman faculty, and enriching them in foundations of machine learning as well as in deep learning. And of course, this AI, ML, and DL, these are all, I'm sorry. And this AI, ML, and DL, they're not the computer science cakes, because one can use this AI, machine learning, deep learning in anywhere, any application they can use. So keeping those points in mind, and last year we started, exploring, machine learning, deep learning, and artificial intelligence in VLSI as well as signal processing. And there are many workshops that we have done as well as seminars, and we are also encouraging our students to participate in the conferences, and so that they can understand this machine learning, deep learning with respect to the electronics and communication applications. So yeah, it's a wonderful FDP topic that they have chosen. And once again, thank you, sir. Thank you very much. So over to PNR, sir.
Madam, Nagajyothi madam.
Okay. Okay, sir. Thank you, sir. Today we had an opportunity to hear your thoughts and experience and suggestions, and this surely encourages us in all our future endeavors, sir. Thank you, sir. Dear, dear
Thank you, madam.
participants, thank you, sir. So this is the time to propose the vote of thanks. I, Dr. D. Nagajyothi, on behalf of EC Department, Vardhaman College of Engineering, and the entire fraternity of the institution, extend my sincere thanks to the Almighty for making this FDP great success. On behalf of our department, I extend a hearty vote of thanks to our resource person, Avin Dayal sir, so continuously spare time from his busy schedule to deliver talk for 6 days. So we got a lot of information which will truly help us in our career. Thank you, sir. Thank you very much for accepting our invitation. So
Thank you,
first
ma'am.
and foremost, it is my privilege to thank our management, Principal Sir, Vardhaman College of Engineering, for giving an opportunity to conduct this event. I wanted to extend my heartfelt thanks to our head of the department, Dr. P. Nageswara sir, for encouraging us to planning and conduction of this event. I would like to thank Dr. D. Praveen Kumar sir, for coordinator of this FDP, for his support and conduction of this faculty development program. I would like to thank our department faculty members for helping us to conduct this event. And last but not least, I would like to thank our students and participants, academicians to joining this session and making this event great success. Thank you very much. Thank you one and all. Have a nice day. Thank you, sir.
So thank
So
you one and all.
dear participants, we can share the feedback link and quiz link in the WhatsApp group. Thank you all.